Good morning.
I can see, let's see, there are usually 200 people, and Eric is the only one who leaves his camera on. Thank you, Eric. It's just you and me talking and a couple hundred people watching us. So
I want there to be some human connection.
I know, really, it's
I mean, personally, I just have a harder time learning without it.
yeah. I did manage to get up enough energy to shave before class this morning, and gradually prepping myself for a return to civilization. Not quite there yet.
I'm gonna say I missed the shaving memo.
Yeah, well, that's all right. You can always, if it gets too bad, you can always turn your camera off. I can't really do that.
It is true. Well, as long as we can hear you, I guess.
Yeah,
and see the little screen here.
See the clipboard.
Yeah, clipboard in your hands are all we need.
Who'd you have for physics 2? Oh, I don't know. It was like this rectangle, just white rectangle, and yeah,
black square with a disembodied voice.
Yeah, exactly. All right, so people are straggling. There's really, yeah, that's true. I could just print out a photo and I could make myself my background and then just.
I believe if I turn my camera off, you'll see that I do have a photo of myself.
Oh yeah, no, just a rectangle. Oh, the shared screen isn't laggy today. All right.
Strange.
Hopefully you didn't jinx us, Alistair. See how it works. And I'm also determined. I have an awesome break. I always say I'm gonna, it's important in an 80-minute class to take a break partway through, and I thought of the best break exercise activity, so hopefully I'll leave myself time to take a short break in the middle. So somewhere around, what time is it? Somewhere around maybe
snack time, like kindergarten.
Exactly. Yeah, I'm sorry. There won't be any juice or crackers or anything like that, but it's a good idea. Well, I think it's a good idea. We'll see if it is. Okay, so let's see where we left off. Right, we've been talking about electric potential, which is mathematically easier than, where the hell is everyone? There's only half the people here. It's Zoom. You just click join. All right. Well, in any case, it's kind of early in the semester to be skipping a class, but whatever. So we've been talking about electric potential, and it's mathematically easier than electric field because it's not a vector quantity. It's just a scalar. And it's the number of joules. If I set up, a bunch of charges here, some minus, some plus around here, maybe I have a charged object like this. Doesn't matter. I just have a bunch of charges. You can ask, how many joules would it take if I took a +1 Coulomb charge and started it from, 1,000 miles away, and I moved it into here, into this point? How many joules would it take to move a +1 Coulomb charge from way away into here? And it might take, if all these charges, if that weren't there, it would take a positive number of joules to move a +1 Coulomb charge to push it against these repelling fields into this point. And that would be the electric potential of this point relative to infinity, because that's where I started. Okay, and so that has units. The potential V at this point has units of joules per Coulomb. Extremely important that you think about that simple thing until it clicks in your head and it makes common sense why that's a good unit for potential or a useful quantity to have. And then, I don't know, I suppose if these were all negative charges, right? If I had a blob here, let's say separate problem, I had only this blob here, which had a bunch of negative charges on it, then all these points around here would all have V would be less than 0 here. And that's always relative to infinity unless we say something else. So, right, because if I had a +1 Coulomb charge way away, it would not take me positive work to bring this thing in. I could just let it go and it would be pulled in here and would pick up some speed by the time it got to here. So because it would be a +1 Coulomb charge, would be dragged in this whole way because the negative charges would be pulling it in. So V would be negative in all these points. And in fact, it'll get more and more negative the closer I get to this. Just like around, say, if I just had a point charge, the potential is positive around it and higher the closer I get to it. And it wouldn't surprise you if I said, look, it takes exactly the same amount of work to bring a +1 Coulomb charge from infinitely far away to any point on this red dotted line. Assume that's a perfect circle. Camera distortion may make it look like less than a perfect circle. So, right, all these points will have exactly the same potential because it will take the same amount of joules to move +1 Coulomb from infinity to here, or to here, or to here. It doesn't matter. And all of these points, all the orange points, will have the same potential as each other and higher than the red points because it's in closer. So this is, and you could imagine a sphere around this thing, and all the points on that sphere would have the same potential as each other, which is what's known as an equipotential surface. And you could ask for the potential difference between the orange circle, a point on the orange circle, and a point on the red circle, right? And I can tell you that if the signs for potential difference, you got to be careful with, and you're going to have to somewhat do it by getting the signs right through equations is very tricky because you'll see the directions of integrals make that tough to do, but you can also just, it works better to just common sense it out. The potential of this minus the potential of that will be a positive number because this is higher potential than that is, right? Because you're in closer. All right. And so obviously the potential of this minus the potential of that is negative. In the same way you do for elevation. If I have a mount, if this represents a topographic map, forget about E and M. If this is a topographic map and I don't know, you have a 10-meter contour interval. So all these points are 10 meter, are the same elevation as each other and 10 meters higher than all the points on that circle. So you know that, this is you can look here and maybe this says, 5,000 meter elevation. You know that this is the elevation relative to the ocean. And then this would be 4990 meters, and that's its elevation relative to the ocean. You understand elevations are always measured relative to the ocean. And so they have an elevation difference of 10 meters, right? So it's not more complicated with electric potential than it is just for elevations. There are absolute elevations and elevation differences. And that connection works so well because there's also, just like here, this point has a certain number of joules per Coulomb, the number of joules it takes to move 1 Coulomb from infinity to here. This point has a certain number of joules per kilogram. It's the number of joules it would take you to move a 1 kilogram object from the ocean up to here. We don't usually talk about elevations in joules per kilogram, but you could, right? Every point in space has a joules per kilogram associated with it if it's, uneven ground. And every point in space, as soon as you lay some charges down, every point in space has a number of joules per Coulomb attached to it. All right, and so that's the scalar field vector potential, scalar field electric potential. And we derived one important result that we're going to use, that we used over and over. If I have a charge plus Q here, the potential at this spot here is going to be K times Q divided by R, where R is the distance away. And so again, that shows you as R gets smaller, as you get closer, the potential gets larger. And we derive that by using integral of E dot ds. And so, right, E is KQ over R squared, and ds was dr. And so we integrated KQ over R squared from infinity into a distance R away. All right. And so then this result we used in a few different places. We did the case where we took a line charge like this. that had total charge Q and length L. And we said, what's the potential here? And we did that by finding the potential here from this little element plus this one plus this plus all of them all the way across. So we did an integral to do that. Same way as we did for electric fields. You have a charged object, you can ask what the electric field is here. That's trickier, or can be trickier, because then you got to worry about vector directions. We also did the problem of if you had, a few point charges. I think we did 6, I don't know, plus Q, plus 2Q, whatever. There were 6 charges like this. And we said, what's the electric potential here? That's easy. The electric potential here. And in this case, here's where you got to be careful. It's not like electric field. If you want the field here, you got to find the vector at this point from this one, plus the vector at this point from this charge, and you'd have 6 vectors to add up correctly. Here, you don't have to do that. Electric potential is just a number. And so I can find the electric potential here from this, which is just K times this charge over that distance, plus the potential here from this, K times this charge over this distance, and do that with all 6 of them, add them up, and I'm done. Okay, so, there's like 50 text messages that I'm ignoring. Hold on. Or chat. Oh, good. People are excited about the cool activity.
Most of them were just talking about joining the meeting.
Yeah. I don't know. Does that, you just click anyway and it lets you join, right?
That's what I did.
Yeah.
Even though it's because it's scheduled for like 2 months ago, it's fine.
Yeah. All right, fine. I'll try to fix that, but I'm always afraid when I try to fix something in Zoom that what I will actually do is break it more. But I'll try. Okay, so let's do, we have to move on to capacitors, but I do want to do a couple more. I'm going to have to make videos for some of the examples we're skipping. And I know I've been promising them, but I really will do them in the next today or tomorrow. But let's do one more. Yeah, actually, there's one example we should do a little in class, because this is also a homework problem. So we're going to look at the potential energy. Sorry, actually, that if we're skipping examples, let me do a different one first. Sorry. Let's look at the example of a, yeah, so before we change gears, sorry. Let's suppose you have a wire. So this is a charged wire coming out of the page. And we need to do this because we're going to do another example that relies on this one. All right, so this is a long straight wire, right? We've done this before. If you have a long straight wire like this, right? So this thing has a linear charge density lambda, and you can say, what is the E field here, a distance d away? Or let's say a distance r away. Right, so and we did this 2 ways. Remember, we did this first with Coulomb's law. We found the E field here from this little piece, and then took only its vertical component because it has a partner over here, and we integrated across the whole long wire, which goes infinitely far, and we found the E field at that point. And then we did it again using Gauss's law. We said we drew a Gaussian cylinder. This is the easier way to do it. We drew a Gaussian surface around it, and we used the fact that E dot dA over the closed surface was Q enclosed over epsilon naught. And so then we found the charge in this, which would be lambda times the length of this cylinder, and then the total electric flux through the cylinder, equated them, and used that to find E. And of course, we got the same answer in both cases, that E the magnitude of E here is lambda over 2 pi epsilon naught R. So the electric field falls as 1 over R around a long straight wire. Okay, so that's not this chapter. That was 2 chapters ago and last chapter. So we did this. So all we're doing in this problem is saying, let's pick this wire up and I'm going to just turn it so the wire is actually pointing at you now. So you're looking end on at the wire. And what we want to find out is what's the potential difference between 2 points, R1. So 1 point is distance R1 away, and 1 point is a distance R2 away. And let's just suppose this is positively charged. So linear charge density lambda. All right, pointing out of the page. So what has a, hang on, let's do polling. All right, so the answer to this is going to either be greater than or less than. And the question is the potential, so this is a positively charged wire coming out of the page, and there is a certain electric potential here, and there's certain electric potential here relative to infinity. So is the electric potential at R1 greater than or less than the electric potential at R2? Okay. All right. Yeah. So most, some, 85, 15%. So good. So right. So the electric potential is larger here, because if this is a positively charged thing, it's going to take more joules to move a +1 Coulomb charge into there than it is to here. Right? Okay. So let's do that properly, though. Let's find the potential difference between these 2 points. How many volts? Remember, our unit joules per Coulomb also is known as volts. Okay, so to do that, we're going to integrate minus E vector dot ds vector from R1 to R2. All right, and the ds vector is dr vector, right, because we're moving in the radial direction. E is lambda over 2 pi epsilon naught r. And so if we do this out, and I'm going to be a little sloppy with the signs, we're just going to know that R1 is greater than R2, because getting the signs right in here is a little tricky. You're going to need to have dr. You really have to move from there to there to make the signs work out. So I just want to show you how basically the integral works, right? So you should have integral of lambda over 2 pi epsilon naught r times dr from R1 to R2. So if you do that, okay, dr over r, when you integrate that, that gives you natural log of r. And so this is going to leave you with lambda over 2 pi epsilon naught natural log of R2 minus natural log of R1, which is natural log of R2 over R1. And then you say, well, wait a second, what's the sign of this? So here's where you want to check it to make sure that it's okay, right? I know that R2 is greater than R1, and so natural log of R2 over R1 is a positive quantity. And I know that the potential here is higher than the potential there. And so this is V at R1 minus V at R2, because this has to be a positive quantity. If you really want to get the signs correct, what you need to do is imagine yourself is get rid of the minus and move from here to here. It's just when you go in the opposite direction to the standard way of integrating, then you wind up with an extra minus sign. So, okay, so fine. So the potential difference is lambda over 2 pi epsilon naught ln of dr2, ln of r2 over r1, which just comes from integrating dr over r. And so this result we're going to use in a little bit, okay? Okay, one other example before we have to move on to capacitors is, sorry, questions here first?
Could you explain that part after lambda that ln, the red part, red hand part?
Oh, from here to there?
No. From here to the red one. Yeah.
Oh, yeah, from here to here. Yeah, so when you integrate integral of dr over r from r1 to r2 is natural log of r2, r1, right? Which would be natural log of r2 minus natural log, sorry, this is getting crowded, minus natural log of r1, but natural log of this minus natural log of that is equal to natural log of r2 over r1.
Thank you. I have one more question is about ds. Could you explain about ds?
Yeah, so ds is the step you take. You take a small, so ds vector, in this case, you move in the radial direction away. So E dot ds, in this case, that's a good question. I should have made that clearer, right? E points this way because we're near this charged wire. So E points straight out and ds vector also points out. So E and ds are parallel to each other. All right.
Okay, so the direction of the ds is outside, right? Outside of that wire.
Yes. Right. It's in the ds is in the direction of is radially away because we're moving from here to here.
Got it. Thank you, sir.
Yeah, and in fact, actually so you could do this problem too, which you'd intuitively know the answer, but it's sort of useful to do it. So you're looking, the line charge is coming out of the page. And if I said, well, what's the potential difference between this point and this point? And you know intuitively that there's no potential difference. And you could say, all right, I'll move from here to here along this dotted line. And in that case, everywhere you move along this line, so here is your little step ds vector, and your electric field here from this points out. So here E dot ds would be 0 because they're perpendicular. And so your potential difference between that point and that point would be nothing. It's the same thing you do if you want to know the gravitational potential difference. Let's say so gravity's pulling this way, and I move gravitational potential difference between that point and that point. And you say, well, mgh and h is the same. But what you're really doing is you're integrating f dot ds. The force points down and you're moving this way. So you're always moving perpendicular to the direction of the force. And so f dot ds in this case is always 0. And so you have a total potential difference between gravitational potential difference between those points of 0. All right? Okay. So one last type of problem. There are a couple more types of problems we should look at before we switch to capacitors, and we have time to do one of them in class, and then one will be relegated to a video. So when look at the potential energy stored in arrangement of charges. Okay, meaning I'm going to take let's say I take a -5 microcoulomb charge, place it here. I put a -5 microcoulomb charge here. And let's see, I want to get the distances of things right. Put +5 microcoulombs here and put +5 microcoulombs there. Okay, and these distances, everything's a meter, just to keep things simple. So that's 1 meter. This is 1 meter. That's 1 meter, and this is 1 meter. Okay, so the question is, how much energy, and let me number these things 1 through 4. Yeah, so call this charge 1, here's charge 2, here's charge 3, here's charge 4. The question is, how much energy did it take to bring these here? Well, I mean, you know, are they all trying to like explode their way out, or are they all pulling each net in? And so maybe it was positive work, maybe it was negative work. Before we do that, let's look at a simpler case. Let's say I take a charge, Q1, place it here. Let's just say that's positive. And let's say Q2 is here, and it's also positive. How much work does it take to put these two here a distance r away? Well, there's not a lot of higher math in this. You just have to think, you know, conceptually what's going on. You can imagine, let's call this charge 1 and that the second charge. So I started with nothing here at all. And I took charge Q1 and I brought it in from infinity and it landed here. That took me no work at all because this isn't there yet. I brought this from infinity and it felt no electric fields because there are no other charges around. I placed it there. Okay, fine. So my running total of energy spent so far is 0. Now the question is, how much energy did it take to bring this in now that this thing is already sitting there? Well, you have to use the definition of potential. You know, so forget about this thing being there. What's the electric potential at this spot, at the spot where this thing is sitting? Somebody unmute. Tell me the electric potential at this spot from this thing sitting there.
It's going to be KQ over R.
Right. K times what Q?
Q1.
Yep. So K Q1 over R. That's the potential here because this one exists. So then the question, and think about the units of that, right? This is not a mathematically hard problem. You just have to think about the physical meaning of the quantity electric potential. So this says it takes K times Q1 over R joules to move a +1 Coulomb charge from infinity to here. So how much energy does it take to move this thing to this spot? Well, it would be, so energy needed would be equal to K times Q1 over R. That's how much energy would be needed to bring Q2 here if it were a 1 Coulomb charge. But it's not 1 Coulomb, it's Q2 coulombs. So it would be that times Q2. So the energy needed to arrange this whole system would be K Q1 Q2 over R. Right? And now if I wanted to bring another, so questions so far on this?
Isn't that almost Coulomb's law?
No, it's not. It's, you know, if it were 1 over R squared, it would be the magnitude of the field. Yeah, so yeah, it's not the field, it's the joules per coulomb to bring charges to here times the number of coulombs that you want to bring here. And then you got to be a little careful. So, but other questions first here so far on this? Okay, so now if I say, all right, fine, now I want to bring another charge. These two are here. I want to bring another charge, Q3, to here. Well, you'd have to say, well, what's the potential at this point now that these two are here? And that the potential at this point would have a contribution from this charge and another contribution to the potential here from this charge. So I'd find how many joules it takes to move 1 Coulomb from infinity to here, and then I'd multiply that by Q3, because that's the number of coulombs I want to bring to here. And that would be the total energy stored in that 3 charge system. So here we can do the same thing, and it doesn't matter what order you do these in, you'll wind up with the same result. So for this, we can just say, if we want the potential energy in this arrangement of charges, let's just do them. That's why I wanted to number them 1 through 4. It doesn't matter what order. So step 1, when I bring in charge 1, my running total so far, I'll write this as energy. Actually, your book, I think, uses U for energy, because E is confusing because you think it's electric field. So the U so far is 0. That's how much energy it takes to bring in charge 1. Okay, now we're going to bring in, 1 is here. These are not there yet. I'm going to bring in 2. So bringing in 2 now costs me, so this would be K times 5 times 10 to the minus 6 coulombs over 2 meters. So that's the potential at this point, because this is there. And I'm bringing in, this is how much it would cost to bring in plus 1 coulomb. I'm not bringing in 1 coulomb, I'm bringing in 5 10 to the minus 6 coulombs. So that's how much energy it takes to arrange 1 and 2. What do you say? I had to multiply Q3 by, to get the, to get the, so Jordan, right, I get the potential at this spot without Q3. I'd just find the electric potential at this point in space, and then I'd multiply that by Q3 to find the work needed to actually bring Q3 there. Okay, good. All right, so so good. This is the energy I've spent so far bringing, putting 1 and 2 in place. And you can see if 2 were a negative charge, I'd get a negative answer for that, which makes sense. It'd have negative total energy that I had to spend to create it so far, because it would have, a negative charge would have been pulled in. Okay, now these 2 are here, and I need to bring in charge 3. All right, so I need the potential at this point, and then I need to multiply it by negative 5 10 to the minus 6 coulombs. So the potential at this point is going to be K times 5 times 10 to the minus 6 coulombs over, so that'll be square root of 2, right? Square root of 2 is the distance from there, so it's K times this charge over distance. And then I have another one of those. I have K times this charge over that distance again. So I'll have it, right, the potential here is twice that, because I have 2 of those charges. So I'll have 2 of these. So this is the potential, the electric potential at that point from these 2 charges. And now I'm going to move in 5 microcoulombs to this point. And so the energy I need to do that is going to be this quantity times 5 times 10 to the minus 6 coulombs. All right, so now this is how much it cost me to bring in 1, and then this is what I spent bringing in 2. Now this is what I spent bringing in 3, and now I have to bring in charge 4. So I need the potential at this point times negative 5 10 to the minus 6 coulombs. So the potential at this point is going to be,
in class.
sorry, what? Isn't 3 negative? Oh, did I write it as a negative charge? Oh, yeah, I'm sorry. I did. This is a, yep, thank you. Charge 3 is supposed to be negative. I was looking at that as an equal sign because I had some other stray mark. Yeah, so very good. Thank you. So this, in fact, this would be the cost to move a plus 5 microcoulomb charge to here, but I'm moving a negative 5 microcoulomb charge, so it'd be negative. Okay. No, it's good that your mic unmuted, Tyler. That's what caused me to actually see that. Caused me to look over and see somebody's comment. Farron, thank you. Okay, so now I need the potential here, and then I'll multiply it by that, and that's the energy I'll need to supply, which could be positive or negative, to bring this charge here in the presence of these three that are already there. So it'll be K times 5 times 10 to the minus 6 coulombs over, so I'm the V here from that charge, and so that'll be square root of 4 plus 1, so that'll be square root of 5 meters. So that's the potential here from this charge. And then the potential here from this charge will be another one of these, right? Because it's a K times same charge over same distance. So I'm just going to multiply this by 2. So now I've done this charge and that charge. Plus, I'm going to move this 4 over. Plus, I need to find the potential here from that charge. So that'll be K times negative 5 times 10 to the minus 6 coulombs over distance from here to there is just a meter. So that's just 1 meter. Okay, so good. So this, keep track of what this is. This is the electric potential at this quantity is the electric potential here because of these 3 charges. And so if I want to move a plus 1 coulomb charge here, it would cost me this much energy. And I don't want that. I want to move in this much charge. This is joules per coulomb. And so I want to move in this amount. So it'll be times minus 5 times 10 to the minus 6. Stella, are you okay with the answers you're getting in chat?
Yeah.
Okay, good.
Thank you.
Okay, so fine. So now we know the energy it took to move in charge 1, charge 2, then charge 3, and then charge 4. So if you multiply all that out and add them up, if you understand this, you don't really have to do all the arithmetic. But if you want to plug in K and do all that out, you should get 0.103 joules. And there is a homework problem sort of similar to this. Okay. All right, so questions so far?
So at the end, are you just multiplying by the charge of the point that we're dealing with? So for 4, for an example, since 4 was a negative 5 times 10 to the negative 6 charge, that's all you're doing to get work?
Yeah, because, right? Yes, exactly. Because think about what it means. That's the good thing. One of the good things about, I like these problems because it forces you to think, to solidify what electric potential means. It means this quantity is the amount of work it takes to move plus 1 coulomb from infinity to this point in space because of these 3 charges. So if you want to move in 7 coulombs, plus it's going to take you 7 times this much work to do it. Because you can imagine moving the 7 coulombs in 1 coulomb at a time. Right, so this thing has units of joules per coulomb. And I say, all right, well, you want to move in this many coulombs. How many joules is it? Well, it's, this times that. And you're traveling 70 miles an hour and you travel for 2 hours, you go 140 miles. So same thing. This many joules to move in 1 coulomb, you're moving in this many coulombs. Okay.
So what quantity is inside the brackets if we don't multiply? What are we finding if we don't multiply by?
Right. If you don't multiply, this is the electric potential of this point in space where this charge lives. Has nothing to do with this charge.
Yeah.
Electric potential is a quantity associated with just a point in space. So pretend there's nothing here. This quantity is how many joules it would take you to move if you wanted to move 1 coulomb from infinity to there.
Thank you.
It's the point of this. It's the electric potential of this point. And you say, well, I want to move this many coulombs. I say, fine. If you want to move this many coulombs, that's how much energy it'll cost you.
Thank you. That makes sense.
Okay, good. Why is U for 1 equal to 0? Because when there are no charges here at all, what's the electric potential of that point in space? Nothing, because there's KQ over R, but there are no charges anywhere, right? We start with a blank slate, and I take that first charge and I bring it into here. The potential of this point in space is nothing because there are no charges around. And so it's zero. So I guess technically it's 0 times 0 joules per coulomb times this many coulombs. Okay.
So quick question. For the electric potential of the fourth one, is that a 2 before the K, the first K?
Yeah, that's there because, right, this, without that 2, this is the potential here from this charge only. And I said, but then we're going to have another one of these from this charge because they're the same and they're the same distance away. So it's really this plus another one of these for that charge. And so
Okay, got it. Thank you.
Yeah.
So at number 4, right? We
Yep,
found
yep.
like the potential from the other 3 charges.
Exactly.
But then at 3, like we only did it from the other 2 charges. Like we were
That's
adding
right.
one charge.
That's right. Because if you're going to build this thing, you're going to have to bring the charges in some order.
Okay.
And so when you were bringing in charge 3, charge 4 wasn't there yet.
Okay. But like, so if all the charges were already there, would 3, 2, and 1 be different?
If all the
Like if we brought them in a different order.
yeah, very good question. That's right. So if you brought them in a different order, you would, let's say we did it 4, 3, 2, 1. So the energy to bring in charge 4 when no charges are there yet, that would be 0. And then now you got to bring in charge 3, and you're going to have some potential here because this charge 4 is now there, and you'd bring in charge 3 and you'd calculate, you'd have a little bit of work to bring in 3. And then to bring in 2, you'd say, well, I got 1 and 2 there. What's the potential here in the presence of these 2? You'd have to find V here from these 2 and then multiply by this. And that would be the work to bring in that. And then this in the presence of all 3, work to bring that in. And we're not going to prove it, but you'll get exactly the same answer. You can do them in any order you want. Right? Does that make sense? Whoever was unmuted and asked that?
Yeah, it makes sense.
Okay, good. All right, and in fact, energy conservation requires that it takes the same energy to do it in any order, because I can guarantee if it took a different energy in different orders, there would be machines that would bring them together in the order that takes little work and then separate them in the order that you get lots of energy back, and we would have free energy, right? We wouldn't need oil or solar or anything else. We would just have huge devices like this that bring charges together in one order and take them apart in a different order. But energy conservation tells you it's not going to matter. You won't gain or lose energy doing it in different orders. Right? Okay. So we need to shift to, we're going to shift gears. However, all right. Hang on, I'm getting the score sheet ready. It is always my intention, like in real in-person classes, I try actually to take like a 3-minute break. Hang on, give me a second to get my score sheet. All right. So from long before your time, and it's actually long before my time too. There was a game called Name That Tune. So you get 1 point. So I'm going to play a song. You get 1 point. And this is perfect. You couldn't even do this. It's one advantage of the whole pandemic. You couldn't do this game in a live classroom because you have too many people yelling out answers. So the first person to type in the name of the song, you get 1 point for name of the song, 1 point for the band. And everyone ready? All right, ready, go. And they're old. All right, Alex gets 1 point. Alex gets 2 points. All right, wait, we have our first points. I'm sorry, there's a limited range of songs. All right, hold on. Yeah, Alex, that was pretty good. Yeah, don't use Shazam. That's lame. Hold on. Alex is faster than Shazam. All right. So Alex has 2 points. Yeah, actually, we may get, there may be bonus points for then singing it, but there's a different better game for that. All right, ready? One more. All right, and go. All right, Joe gets one. Band or singer? All right, Joe gets 2. All right, cool. I haven't figured out what the prize is going to be yet. Oh wait, no. Is Jordan got the band? All right, hold on. All right, stop typing. I don't want to lose track of who got the first JP. Apprentice. All right, 1 point. All right, we got to do one more. Hang on. Ready, go. I may have to advance this one. This isn't a work. All right, geez, Joe, you're quick. All right, wow, that was faster than I thought. All right, hang on. Nobody type anything. I can't, otherwise. So Abby was first to type for band, and Brady Madden was first for, all right, so Abby gets 1.
Personally, I'm disappointed in my own song knowledge.
Yeah, in your what?
In my own song knowledge.
Oh yeah, all right, that's fine. These people are fast. Hold on. Who was first? Brady Madden. All right, we'll be thinking of glamorous prizes for the winners. Yeah, Robert. No offense if you weren't told. Maybe this would be easier. How do I kick you out of the meeting?
You click the 3 little dots up in the top right corner.
Oh,
of their box.
perfect. Well, it's hard. The weird thing is that, right, these songs are like, people know songs that are much older than they are. When I was in college, nobody knew songs from 30 years before they were in college.
It's the internet, I guess. If
I
you
don't know
really
if
like big band, you can listen to it.
Internet or, all right, hold on. So we need scores. All right, we're going to go back to physics now.
I like that idea.
All right, we'll get some sort of engraved mug. Yeah, exactly. Thank you, Trevor. If people are guessing them, they're not too old. Yeah, I'm trying to put ones that are kind of still known songs. So, all right. These are great songs. Facts. Okay, good. Thank you, Jordan. Thank you for defending the song choice. All right, so questions on physics or music? Yeah, I didn't have, oh yeah, I will add a Billy Joel in there somewhere. It's compressed audio and just the intro. Yeah, and no using, how fast is Shazam? I guess not as fast as Jordan. Yeah, so, all right, good. Yeah, Jordan, several of you are faster than Shazam. I guess, all right. Yes, Daniel, you'll eventually get a point. All right, so let's shift gears from electric potential to capacitance. All right, so in fact, hang on, why is this thing doing this? All of a sudden my screen is going crazy. Sorry, give me 1 second. All right, okay, I guess it's back. All right, so we're going to look at capacitance, and by that we mean capacitors. Right, so a capacitor is an object that has a certain amount of capacitance. And what we'll learn in a little while is the capacitance of an object depends just on the geometry of the object, but we'll get back to that in a minute. So the obvious question is, what's a capacitor? Right, so basically the simplest capacitor, so a simple example is just two parallel plates, right? So just parallel plates. Okay, and I'm going to take this plate and I'm going to put a positive charge density on it. A positive surface charge density, let's say plus sigma. And on this plate, I'll put negative charges. That's not a 0, that's a sigma. And on this plate, I'll put negative, the same charge density. And so this plate has a surface charge density of minus sigma. All right, these two plates form a capacitor. They actually form a capacitor even before I put any charge on it, but typically you have charged capacitors. Okay, you could also then take these two plates and I could, let's say I could put some insulator between them so they don't touch and share the, and discharge to 0. I could take a, I could roll them up like this and have one of the plates like that and the other plate like this, just held separate from it. And so this is our positive charge plate now rolled up, and this is our negative charge plate rolled up. So in fact, when you tear open any electronic device and look inside, and you see, often you see little things like this. You see some little cylinder with two wires coming out, or if you're in lab, I guess lab must be crazy now with, right? It's hard to do lab over Zoom. Right, so if you have if you have a little cylinder like this with two wires coming out, odds are good it's a capacitor. It's basically, you take two little ribbons of conductor next to each other, charge one, and then roll them, put in some insulator between them, and then roll them up and stuff them inside some insulated cylinder, put a cylindrical insulator around it, and you have a capacitor. Okay, so what do they do? Their purpose is to store charge. So throughout this course, we're going to look at capacitors, resistors, and inductors. And so this is the first of those. So there are many other purposes, but for our story right now, their purpose is to store charge. How do they store charge? Well, if you think about it, suppose I took a battery with 9 volts of potential difference. Now you know what volts are at this point. That's joules per coulomb. So you take a 9-volt battery, that means the positive terminal is 9 joules. It would take you 9 joules to move 1 coulomb of charge from the negative terminal to the plus terminal. All right, and let's suppose I wire that like this. And no matter what the shape of an actual capacitor is, we always just write them in circuits as 2 parallel lines. Now be careful, voltage sources are also written as 2 parallel lines, but they're uneven length, with the plus side, the positive voltage side being longer than the ground side. Okay, so here is our capacitor. Okay, now here is one very important point that comes up over and over and over in all of our circuits. I want you to imagine what you really got is a wire here, maybe soldered onto this metal plate of the capacitor. What's in front of the V? Yeah, that's a 9. So I just said it's a 9-volt battery. So what I want you to remember is this is all one piece of metal. The plate of this capacitor and this wire, and then it's all attached to this piece of metal. So you could really think of it as you could have formed this whole thing out of one blob of metal. You could have melted it to make a long, thin strand, and then flattened out this end to make a plate, and flattened out this end to make one side of the battery. So this is all one piece of metal, and what you know about metal is that it is an equipotential. Everything on the surface of metal is the same potential as each other. And if you don't remember that, you say, well, why would that be true? Because there are no electric fields in conductors. And so if I have a metal blob like this, there are no electric fields, which means there can't, this spot and this spot have to be the same potential. Because if they weren't, right, if I do E dot ds along here, it'll be 0 because the electric field is 0 everywhere along here. So there is no electric field, so it would take no work to move charge from here to there on a conductor. Basically, it's the charges aren't moving around, they're all done moving on a conductor. And so this is all one potential. And this, so everything in blue is at 9 volts. And everything in black is at 0 volts. All of this and the wire and all the way to there. So that means there are 9 volts of potential difference here, but because this is wired straight to that and this is wired straight to that, this thing also has 9 volts of potential difference. All right. So questions so far? Okay. Good. So there's 9 volts of potential difference here. And now this is, you got to be careful because this is the point of the definition where people get a little confused and it can look like it's upside down. The question is, so what do you think happens if I attach this to this battery? This is the plus side and this is the negative side. And so what you get is positive charges flowing onto this side of the plate. And so I'll be left with a bunch of positive charges here, and I'll be left with negative charges on this plate. And that makes sense. That's why there's a potential difference between those two plates, right? So if let's in fact go back, let's take one step back. If I have this plate with charge plus sigma and this plate with charge negative sigma, let's think back for a second to what we had. If I just had this plate with charge sigma on it, the electric field here from this plate, let's say that's positive. So this has a plate with surface charge density, you're looking at the edge of it. Surface charge density sigma. The electric field is sigma over 2 epsilon naught, the magnitude of the electric field. So it points this way and it's sigma over 2 epsilon naught. And we derived that with Gauss's law. Remember, we did like a cylinder going through it. So the E field near this plate of surface charge density sigma is sigma over 2 epsilon naught. Okay, so good. So so if you're standing here, there's an electric field that points this way from this plate. There's also an electric field that points this way from this plate because the E field points toward this negatively charged plate. So the total E field in here is going to be sigma over epsilon naught, because you'll have sigma over 2 epsilon naught pointing away from that and sigma over 2 epsilon naught that would be the contribution of the E field here from this plate. And so the total will be sigma over epsilon naught. And so what you know, in a common sense sort of way, the more charge I put on these things, the stronger the E field is. You don't need to probably take physics class to know that if I load these up with tons of charge, it's going to make a really strong electric field from there to there. And so the more charge I put on this, the stronger the field is, but that also means the larger the potential difference between those two plates is. Because now picture putting a ton of charge on these and then trying to move a +1 Coulomb charge from here to there. It would take a lot of work because you have a very strong E field and you're trying to move that +1 Coulomb charge from here to here in the E field. Okay. Okay, so questions so far? We're about to get into the definition of this, but just questions on what's going on so far? Okay, so what we know so far is that the voltage difference between these two plates is going to have to match that voltage difference exactly, because this is all one conductor. And what we know is that charge is going to build up on these. And charge is going to build up on them until this potential difference is exactly 9 volts. So then there's the one big obvious question, which is how much charge? How much charge, if I take 2 metal plates like this and attach them to a 9-volt battery, yes, they'll flow charge until the field is strong enough that there will be 9 volts of potential difference between them. How much charge does that take? 1 coulomb, 7 coulombs, I don't know, 9 coulombs, right? So how much charge to get some potential difference across the plates? And we always, when we talk about potential, we always talk about potential relative to something. It's like talking about elevation. You talk about elevation differences, or you can only talk about absolute elevation if you've already agreed upon what the zero is. We don't always say over sea level because we just understand that. Does that mean the capacitors will discharge periodically? They'll discharge only if there's some conductor. So Robert, yeah. So if you put a wire between these two, then they would discharge. And in fact, then it would just keep flowing current. But no, if there's just an empty gap, they won't discharge. If there's a vacuum, the charge will just build up on it and then just stay there. Right? You'll just have a permanent electric field going this way. And then it would cost you a certain number of joules to move a coulomb from one side to the other. So the answer to this question depends on the object. And that's the definition of capacitance. So capacitance is defined as Q over V. And it is the amount of charge. Sorry, I have to write this here. So the definition of capacitance is the amount of charge needed on object per volt of potential difference across it. Right? So, of course, if I put 100 volts across this, it's going to take a lot more charge before I get 100 volts of potential difference between there and there. And if I put 1 volt, it'll take 1 volt across it, it'll take less charge. But we're going to find that that's a linear relationship. If I double the charge, it'll take, I'll have to put twice the, if I double the voltage, I'll need twice the charge on this to get that voltage across the plates. And so it's that ratio that is the capacitance of an object. So capacitance is a property of an object. It doesn't matter what circuit it's in. It is a property just of an object, like its mass, its radius, its density, whatever. Objects have a specific amount of capacity that depends on what their shape and size is, which is why when you go into the lab, you can pick up, or when you watch somebody else on your Zoom video of a lab, you can look at a thing and it will say that there's a certain number of the units for capacitance or farads. And it will say this object has a certain number of farads of capacitance. All right, so this will make, I hope, a little more sense as we do an example. Right?
That line at capacitance is pointing at the Q or the entire equation?
The whole thing.
Okay.
This is the what capacitance means. When you say, what's the capacitance of an object? If I take two plates and hand them to you and say, what's the capacitance of this? What I'm really asking is, how much charge would you have to put on the two plates in order to get 1 volt of potential difference between them? That would be the capacitance of the object. And so we're going to compute capacitance for two parallel plates in order to sort of solidify this definition. And in fact, a farad is a huge amount of capacitance. Real, ordinary lab-sized things have capacitance in like nanofarads or picofarads, 10 to the minus 9 or 10 to the minus 12 farads. Is this similar to Ohm's law? Not really, Evan. It's not. No, I would say no for now. I mean, it's also linear, but that's a different thing. So Ohm's law relates to resistors. Okay, so with this, so other questions so far? Okay, so let's find the capacitance of two parallel plates. And we said capacitance is just a function of the geometry of the objects. So let's say I have two plates and they each have surface area A, and they're a distance d apart. So let's actually, it's very confusing to look at it that way. So that's what they, I got a plate here and a plate here, and they each have surface area A, and there's separation of d between them. So let's just look at that edge on. So here's a plate with surface area A, here's another plate with surface area A, and there's a distance d between them. All right, this is the critical point. If you want the capacitance, you're asking, how much charge do I have to put on these in order for there to be 1 volt of potential difference between them? And you know that it's going to, getting a volt of potential difference between them is going to depend on the charge. Because if I put, just imagine I put the tiniest amount of plus charge, really not very sparse plus charge there and hardly any negative charge here. Without taking a physics class, you know that the electric field is really weak now. Yes, it's still, there's an E field that points this way, but it's weak because there's hardly any charge on here. And if it's a really weak electric field, it's not going to take me much work to move a +1 Coulomb charge. If I grab a +1 Coulomb charge, it's not going to take me much work at all to push this +1 Coulomb charge from there to there. Right? And so, so clearly the voltage difference between these depends on how strong the field is, and how strong the field is depends on the charge density. And so it's that relationship that we want. C is Q over V. So we're asking, how much charge am I going to have to put on these plates of surface area A, distance d apart, in order to make it 1 volt of potential difference between them? All right, so let's try to calculate that. Well, what I know is that if I put a surface charge density plus sigma there and minus sigma here, I know the electric field here, anywhere in between them, is sigma over epsilon naught. Because the E field here from this plate is a half sigma over epsilon naught that way. The E field here from these charges is a half sigma over epsilon naught. And so that combined, they're basically working together. And so the total electric field in here is sigma over epsilon naught. Okay? So questions so far? Okay, so potential difference between the plates. Well, that's just going to be, the electric field is constant. So yes, in principle, we have to integrate E dot ds from there to there, but E is the same everywhere in all of these steps. And so the potential difference between the plates just becomes E times the distance between them. Okay, and the electric field, we already know the electric field is sigma over epsilon naught. And so that is sigma over epsilon naught times D. So that's the potential difference between the plates. And it makes sense, right? That the bigger sigma is, the larger the potential difference between these two things, between the two plates. If I put a ton of charge on these things, then it's very large potential difference between them. It would take a lot of work to move a +1 Coulomb charge from there to there, because there's a big electric field pushing that way. That would be pushing it that way. So this is the hardest part of the, mathematically, it's not a very advanced problem, but conceptually it's subtle. That's the potential difference between the plates. Questions so far? The way we should write C to differentiate from coulombs? Yeah, no, not really. It's just context, unfortunately.
Wouldn't you be able to cancel the D in this situation?
Well, we're gonna. No. We're just moving forward. We're not right. We already, if we cancel the D, that just tells us that E is equal to sigma over epsilon naught, which we know is true. But in this case, we really want E times D because we want the potential difference. Okay, so good. So here is the potential difference between the plates. Fine. So now what's the, we don't want that. We want to know how much charge we need and to get 1 volt of potential difference between them. So there's the potential difference. So V, I don't want to rewrite that whole thing. So I'll say V diff is sigma over epsilon naught times D. But sigma is Q over A, the surface area of the plates. So I'm going to write this as Q D over epsilon naught A. All I did was say sigma is Q over A. All right. Okay, so somebody tell me how much charge, so take a second on your own. So the potential, this relates the potential difference between the plates to the amount of charge I put on them. You tell me the size and distance apart and area of the plates and how much charge you put on it, and I'll tell you the potential difference between them. So my question is, just take a second and this is not a long problem. How much charge needed to get 1 volt of potential difference between plates? Just take a second, do it on your own. I want to know the amount of charge in terms of what variables we have to get 1 volt of potential difference between the plates. All right, what's the answer? Come on, somebody unmute. I want 1 volt of potential.
Would it be E naught A over D?
Yep. Epsilon naught A over D. That's the amount of charge. If you say, I want to put a voltmeter on these things and I want it to read 1 volt. Tell me how much charge. That's the amount of charge, right? You just set voltage difference to be 1 and solve Q, epsilon naught A over D. That's how much charge I'd need to put on them. Now, suppose I then said, okay, I want 5. I've decided now instead I want 5 volts of potential difference between them. How much charge do I put on?
Just 5 times epsilon naught A.
Yeah, exactly. I want you to do 5 times. So for every time I add this amount of charge, I increase the voltage across them by 1 volt. So the ratio of how much charge I need to put on the object for every volt of potential difference I want across the plates, that's the capacitance. And it's epsilon naught A over D. How much charge I need for every volt of potential difference I want across it. And so now, questions on this? Okay, and so now you can see the difference between a big capacitor and a small capacitor. If I take a 9 volt battery, or whatever, any voltage battery, and I put it on a capacitor that has a small capacitance, that means for a given voltage across it, I only need a little bit of charge. So if I hook a small capacitor up to a 9 volt battery, it's only going to store a small amount of charge because it only takes a tiny amount of charge before it already has 9 volts of potential difference across it. If it's a huge capacitor, then it's going to take, yes, it'll always be 9 volts across it, but it's going to take a ton of charge before it gets 9 volts of potential difference across it. Okay, so one thing, and this you're going to have to mull about. This is a subtle question. If you look at this, so question so far? Yes, and that's in farads. It's always in farads, Alistair. Yep. So a subtle question, and I'll give you the answer now, but you'll probably have to mull it over. There's something interesting to notice in this. If I shrink D, if D gets smaller for an object, because remember, capacitance is a property of an object. So if I have these 2 plates, they have a capacitance, and that's it. So what's interesting is if I take these and I move it so these 2 plates are now closer together, let's say I move it so now their distance between them is D over 2, their capacitance doubled. That's kind of weird, right? You take 2 plates, I put a 9 volt battery across it. It's going to take a certain amount of charge on this and this before I get that 9 volts, and I could find that from the capacitance. If I move them closer, now if I cut the distance in half, it's now going to take twice as much charge. It's now going to take twice as much charge to get the same voltage across them. Hang on, there's a couple of questions. How are C and Q the same equation? Oh, yeah. So this is the amount of charge Q needed for 1 volt of potential difference. Right? So this is the charge needed for 1 volt of potential difference. And it's that relative amount that gives you capacitance. And so you can think of capacitance also as being the amount of charge you need for 1 volt of potential difference. Okay? So Eric, did you have your hand up?
I thought I had an idea of why it would be doubled.
Oh yeah, go ahead.
Well, since the plates are closer together, wouldn't the charges, like, I'm just going to say want to, because in lack of a better term, want to move more?
Sort of. A little, although not really, because right as I move them closer together, if I just take 2 plates with fixed amount of charge on them, if I move them closer together, the E field in between isn't stronger. It's still just sigma over epsilon naught. But what happens, and I'm sorry, I would normally give you more you guys more time to answer, but we're running over, well, we're just running out of time. Here's the issue, and we'll talk about this more next time. If I cut the distance in half, and this is a subtle thing I really want you to think about. If I cut the distance in half, the E field is still sigma over epsilon naught in here, but now there's half the distance, which means the potential difference is now cut in half. Right? It only takes half as much work to move a +1 Coulomb charge from there to there as it
That makes a
did
lot
when
more
they were
sense,
from here to
actually.
here. So it's only, so here's the key point. It's only when I do this with the same sigma, I just cut the voltage in half. So if you want to keep the voltage at 1 volt, you're going to have to pile up twice the charge density to do it, because you're going to have to double the strength of the E field because you're only moving your +1 Coulomb charge half as far in it. And so you'll now need twice the charge to get a volt across this that you did here. You'll need twice the charge density and hence twice the total charge. So in fact, when you see, so in real capacitors, what they do is you take like a little piece of foil, and then, because you don't want your capacitor to be huge, because you don't want your phone to be this big, you actually take one piece of conductor and you coat it with a very thin insulator, and then lay the other conductor on top of it, and then roll them up to make it as small as possible. Because the closer you can get those two conductors, the more charge they will hold for every 1 volt of potential difference across them. Okay, so I will post some videos, but between now and Tuesday, be sure you spend a good amount of time working on the capacitance chapter, okay? And I'll see you on Tuesday or in office hours. Just sit in labs. Roy's taught to handle capacitance in microfarads. Yeah, plain farads are dangerous. That's a huge capacitor. It would hold a huge amount of charge, right? And by the way, if you've sent me an email and I haven't answered yet, I will. I have like 40 emails to answer. Yes, office hours 1:30.
Have a good one.
All right, bye all.